So you were saying that we are at the half-life of our biosphere.
Depending on which models you use, yes.
Okay, well, so roll with that then. So you were saying life has been on Earth, where you're saying 500 million years.
Yeah. So the Cambrian explosion, which is where you had the transition from like simple, basically single cellular life, as it starts getting complexifying and turns into the macroscopic multicellular life that we have. That happened around 500 million years ago, right? Now, again, depending on the models that you use, and like I said, there are reasons why this model may be incomplete. So take all this with a grain of salt. As the sun expands, as the fusion fuel of it starts to run out, the sun's going to heat up, it's going to expand, and the surface of the sun is going to creep slowly towards our position in the solar system, right? So as that happens, the average temperature of the planet is going to start going up, and it's going to get to a point where, and again, this is still going to be way before the planet's engulfed by the sun. This is still way before that, but the temperature will get to a point where it's going to start evaporating the water on the surface. So slowly, oceans are going to go the way of the dodo, and we're going to look a lot more like Mars before the planet itself is given the kibosh. So really, when you look at that timeline from 500 million years in the past is when complex life had its start, to 500 million years in the future, that puts us right dead smack in the middle. So you can think of it as humanity is currently in the middle of its midlife crisis. So really not even humanity, complex life on this planet as we know it. And that, to me, seems like a pretty good motivation that we should start to take this more seriously as a species. Yeah. And so you're saying we need to get off this rock. I think that's kind of the prevailing theme. Yeah, we got to get off this rock. Yeah. Or, well, go to this rock in a different time, but that's we'll get into that later. Well, and so you have been doing warp drive research. That is your thing. You're doing mostly mathematical physics. You were not a PhD physicist. No. But you are, like, I would not say enthusiast. I don't think that does justice to your work. You're working with Dr. Jacques Sarfati. Loosely. Collaborating with several other well-known physicists. Depends on his mood that day. It's for all of these. So, what are your thoughts on this? I mean, do you think that this is something that's achievable? I guess? So how do we get off the rock? That's the big question that we need to get off. So the next question is how. I don't think chemical rockets are the way to go. There's just the specific impulse is too bad for us to really get out of the solar system within any meaningful time, unless we're going to do generation ships. And there's still problems to have with generational ships that I don't really want to get into. So really, we're only left with a few options. We might be solar sails, but even though that's still looking at a generational ship, really what we need to be looking at is space-time metric engineering is what the newer term for this. The lowbrow term for that, anti-gravity, even though I hate that term. Well, and anti-gravity, yeah, it's a science fiction term. A lot of scientists kind of they look sideways at it at the very least. They defend it at the most, and it doesn't necessarily really describe what we're looking at, because we could be looking at a variety of reactionless propulsion, field effect propulsion, some kind of new form like space-time vacuum metric engineering, right? I mean, there are a lot of different things there, but so before we get into UFOs, UAP, whatever acronym we want to use specifically, let's talk a little bit about general relativity in its sense, without going into a side lesson on what general relativity entails. It being our theory of gravity, our most successful one, it has had a lot of predictions, and just about every prediction we've made with it has been confirmed as true, right? Okay. So what are some of the predictions that general relativity has made? Well, one's been gravitational waves, another one's been the expansion of the universe, another one's been black holes, right? So there's three good ones. Very recently, pretty much all of these have been confirmed one way or another. So for probably 90 years, people would go, black holes, it's just a theoretical mathematical object. It pops up in our equations. They don't actually exist. I'm sure people have heard that. The farther you go back in the literature, back then they weren't, actually it was John Archibald Wheeler who coined the term black holes. Before that, they were just called Schwarzschild objects. But I mean, we've seen the vacuum jets in our radio telescopes, right? Yes, yeah, and that's what I'm getting towards. So you have these very clear objects, these very clear predictions of general relativity that says these things are possible. If you look for them out in the universe, you're probably going to find them somewhere, and they're not going to break the laws of physics. So we've been able to simulate these to very high fidelity, let's use the movie Interstellar, for example.
Yeah.
That has been a great visualization of what wormholes and black holes can look like. And the reason they did that is because they worked with Kip Thorne to actually get the physics right on the movie. So what you see on the screen in those movies, those are the actual physics simulations of what we think they would look like. And if you're familiar with I think it was 1 or 2 years ago now, when we finally got the pictures of the M87 black hole, and it looks like our simulations are really good at what these things would probably look like. So black holes, confirmed they're real. What's on the inside of them, we're not going to talk about that right now. That's a different conversation. Which actually we'll probably get into that at some point, because I'm digressing too much. Anyways. So another one of the expansion of the universe, which was confirmed, I think, finally by the CMB in 1997 and 1998 when they got the information from that telescope. So you have the expansion of the universe, the prediction of general relativity we confirmed is real. The black holes, these are just more out there predictions, or I don't want to go into the precession of Mercury and how relativity explains that, but Newtonian physics doesn't. You can find whole lectures on that. And so then the third major prediction was gravitational waves. It was another one of those things where people said, oh yeah, they pop up in the equations, but there's really no way that we'd ever be able to, just mathematical formalism, but let's not worry about it. Well, from the LIGO and Virgo detectors over the last, I don't remember the exact year they started popping up, but we've now been getting images, which are really not images.
So we have black holes, we have cosmic expansion. These are things that show us that the vacuum can be manipulated, right?
To a degree. So that's kind of what I was getting at with the gravitational waves. So we've confirmed gravitational wave. We've observed them with our interferometer observatories there.
Yeah.
Now, and this will start getting into a little bit into Jack Sarfati's work, which will segue nicely into warp drives. But let's not even talk about Jack for a second. Let's talk about the other person that came to predict essentially the same thing as him, Ray Chow. Okay, he's been working with Ray Chow, and I believe 2002 was when Ray Chow first wrote up the formalism for this. I think he called it like the gravitational permeability or something like that, or permeativity. I can't really recall the exact terminology that he used, but basically, as time has progressed, he's basically said, the only way that we'll actually be able to detect these gravitational waves, if they exist, is if you have the permeativity or permeability of gravity that's actually adjustable. Okay, if that wasn't the case, we wouldn't be able to observe these. So now segueing into Jack's work with UFO as well. What Jack's whole thing is warp drives. Right.
Yeah.
What is a warp drive? It's based on the work of Dr. Miguel Alcubierre, who in 1994 he wrote up the first paper. It's called Hyperfast Travel Within General Relativity. It's right here. I could probably pull up the exact one if you wanted the exact name, but that's neither here nor there. People can go look up the paper.
Yeah, and now in Miguel's case, his stated goal outright was he wanted to find a way within known physics to basically create the Star Trek warp drive.
So Star Trek was one of his influences. There was another one that most people don't talk about because it's more nerdy and it doesn't have to do with Star Trek. That was the expansion of the universe itself, how it seems to be expanding faster than light at the edges. So that was his other motivation, is to, it seems that space-time can be used for apparent superluminal travel within certain contexts.
Okay.
So really all Alcubierre did is he introduced the formalism for other people to build off of in successive works. This is in 1994. This is 30 years ago. We've had 30 years of different people, writing different papers where they've been able to drive down the energy requirements, yada, yada, yada. Now, there are certain reasons why the Alcubierre solution specifically is unphysical. We can talk about positivity conditions aside. That's another conversation on whether or not, what people are going to choose to believe about what kind of positivity and conditions we may or may not have to impose. the major positivity conditions aside from Alcubierre is just the vast amounts of energy required. So it was 10 times the amount of energy in the observable universe, and then an equivalent amount of negative mass. You're never going to get that much energy somewhere. Now, there's been a bunch of papers, which I have in here. Let's see, yeah, Alcubierre and derivatives. So you have a bunch of people. Yeah, so warp drive, hyperfast travel within general relativity. That's Alcubierre's first paper. You start going into the rest of these, and what people have started doing is they've basically been, let's say the energy requirements for Alcubierre are a tree, right? What these other physicists have been doing is they've been taking an axe to the tree, and they've been chipping away bits at it, a little bit at a time, a little bit, driving those energy requirements down. Now, Dr. Harold Sonny White, which we talked about earlier, and depending on what you
yeah, and again, so he's working on EagleWorks, NASA's EagleWorks. That's pretty well known.
And so one of the things that he talked about that we can do to lower these energy requirements was well, first thing he did is he made the bulb. So Alcubierre's bubble is very thin. He makes the bubble itself thicker, and that works to drive down the energy requirements because the densities themselves actually aren't as high.
Okay.
The other thing that he did is he actually kind of like pulsates the field and vibrates it, and that somehow or another that softens the permeability of it or whatever, and it makes it easier, or makes it more elastic, easier to stretch. And what he was able to do is he was able to drive down the energy requirements. Now remember, we started in 1994, what the energy requirement started at 10 times the amount of energy in the universe. No one's ever going to get there. What people have gotten that down to is now about 700 kilograms of mass energy, which is orders and orders of magnitude less energy. And that was, I think, 2012 is when that. And excuse me, I've heard of other people getting it down lower. Gianluca Pierciano, who I have papers in here, he talks about getting it down to a quote-unquote arbitrary level. You'll have to ask him what he means about what he means by arbitrary. I don't know if he means it's arbitrary for us to produce this amount of power, or you can do it with next to little power. I don't know. You'll have to ask him that, not me. But really what we're getting at here is that to reel this back into the predictions of general relativity, what warp drive is it is another prediction of general relativity. It is a prediction of our most successful theory to date, quantum mechanics aside, but we'll probably get into that later. And so there's nothing against a warp drive in our laws of physics. There's nothing saying that can happen. And there in itself, it is an engineering challenge.
Okay.
Now, that being said, looking at observations, do we know of anything that fits the observational parameters that you would expect one of these things to kick off?
No. Dr. Kevin Knuth has said that UAP may fit those parameters.
Not only Dr. Knuth, Sarfati, just a whole plethora of them have gone through quite a few reasons as to why the 5 observables, or 6 if you're talking to Sarfati, because he adds on another one on top of that. They overlap exactly with the expected signatures that one of these structures would give off.
And actually, if I could add something in, one of the things that has intrigued me, the Scientific Coalition for UAP Studies, the SCU, is pretty well known for the Aguadilla, Puerto Rico UAP sighting. This was a drug interdiction aircraft, U.S. government,
where it goes under. Yep.
Yeah, and so it had a top-down view of the UAP. So analysis of this video seems to indicate what could be gravitational lensing, and that would go exactly to what you're talking about in terms of warp drive.
Yeah, and so like what are the 5 observables going off? I have them listed in here somewhere. I just instantaneous acceleration, hypersonic velocities, positive lift, anti-gravity. I think the 6th one that Jack added was like blue shifted radiation and effects adding on people. I think I already said instantaneous acceleration. What was the other one? Transmedium.
Yeah, transmedium travel. I'm getting lost also because there are a lot of add-ons, and this goes somewhat off the topic, but depending on who you talk to, right? Biological effects on bystanders has been considered one. That's not one of Lou Elizondo's originals.
No, so that was the 6th one that Jack added. Yep.
Yeah. So there are a lot of it's starting to blur out out, I guess, as more people have input into what defines UAP.
Yeah, and so one of the things of the OSAP program, AAWSAP, that was ran by James Lukatsky, I think it was started in 2007 is when that started, 2007, 2008. They contracted a bunch of the Bigelow research program was part of this. They kind of, and Puthoff was involved with that. They basically, and I'm probably going to get some of this wrong, and there's going to be people who are going to start flaming me in the comments for brushing over and paraphrasing some details. Essentially what their job was is twofold. One, cataloging the effects that people are getting off these UFO sightings, particularly within the military. That was ATIP's job, which was the Elizondo's. OSAP, they branched out a little bit more. Another one of them was extrapolate your, let's just say you guys are some of the physicists that are part of this program. Let's look at your field of study. So you say your field of study has to do with propulsion systems and energy, yada yada yada. Where is your field going to be in 50 years if everything goes the way, everything goes how it's supposed to? And what they came to is the conclusion that these are probably warp drives, as put out by Dr. Alcubierre. And so, you were about to say something.
This kind of works both ways, right? So not only does that indicate that warp drive is possible, and hopefully possible within, kind of the volume and the structural requirements of, spacecraft as we know them, it also says that UAP are probably using warp drives and reinforces the extraterrestrial hypothesis.
Potentially, yes. So how do I want to word this? We see that these things, the things that they're doing, they overlap. The 5 observables overlap exactly with the predicted observables of an Alcubierre-like metric. Now, this has again been reinforced by the statement of David Grush, who has gone out of his way to say explicitly, we do have physics explanation for these. These are obviously, Alcubierre-like systems. Is the terminology he uses. I think it was Jesse Michaels' video that. It was his clip of that. So you can go and find that out there in the out there in the ether. So the fact that we have. So let's think about what are some other possible explanations that could explain some of these UAP observations. We can come up with a bunch of things that might explain 1 or 2 of the 5 observables, right? But what fits all 5 of the bills? Now people will start coming up with this is where, and I see this in the media all the time, and it drives me up a tree. UFOs defy the laws of physics. Physicists need to go back to the drawing board to think up new physics to explain UFOs. No, that's all bullshit. Excuse my French. They're ignoring the warp drive aspect. Yeah,
I would say the best that you could say is they defy the laws of traditional Newtonian mechanics.
Yeah, they defied Newtonian. That's more accurate.
I think what you were driving towards, and I tend to agree with this, and I think Jack does as well, and many other people, is it seems to fit perfectly with relativistic physics.
Perfectly. And really, we shouldn't be invoking new physics if there's no reason to.
And relativistic physics is the one that would govern warp drives and gravity modification, right? So
you have this thing that fits the bill for the observations, and it doesn't defy the laws of physics at all. So Occam's razor dictates that's the one that we should be pursuing at this point. We have things out there where they show obviously these type of mechanisms are possible if these things are going. When you have something that's Kevin Knuth on his which is in here. Let's see what do you have that listed as? I think it was estimating flight characteristics. Yeah, 5,000 Gs. 5,000 Gs is stupid.
And to add to that a little bit, one of the things that Kevin Knuth has talked about is measurements by Hermann Oberth going back to the 1950s.
Yep.
And so one of the things that drives me up a wall is this idea that these are quote-unquote black projects, and that's why we should just dismiss this as something that our illustrious military has cooked up to do X, Y, and Z. But the challenge becomes, not only do these effects go far beyond anything that traditional airframes are capable of, right? Which would, even if they had an engine that was capable of it, the airframe itself would collapse with that kind of acceleration.
With the G-forces, yeah, it's just going to destroy itself.
It goes beyond other known variables, like for instance, if you're traveling at those kind of speeds, accelerating at those kind of speeds, you would have a fireball, and that is something that Avi Loeb and Dr. Sean Kirkpatrick described in a paper that they did, I believe, about a year ago. So there are a lot of anomalies there that rule out human technology.
And then even vying in with like going off Kevin Knuth's work, I don't believe that he's published this yet. But it was part of the UAP expedition to Catalina Island when they were getting when they were getting I know I saw him say this in an interview somewhere, but one of the observations that they were able to get from 2 different camera angles on 2 different types of cameras is one of these objects which appears to have a blue shift in the front and then a red shift in the back, which is exactly what you would expect from an Alcubierre Drive.
Okay.
And so we're getting more and more data trickling in that this is the way that we should be doing. So really, we shouldn't be wasting money on chemical rockets and putting hundreds of billions of dollars in research into this if we know it's a dead end.
Again, I've been in this area for 22, 25 years now, something along those lines, and what I have noticed is when I first got into this, it was very much kind of a fight the power mentality, right? And I think that in some ways, that rebellious innovation is healthy and justified and necessary. And we see that with breakthrough technologies like Tesla cars, EVs, right? Where, that determination to do things differently can make a real positive difference. But one of the other things that I have seen is for any kind of technology cycle like this, you have initial stages, and then you have widespread adoption. It hits peak maturity, and then eventually it's replaced as the need becomes apparent that there's something better needed. And in the case of rockets, now we are seeing them used more widely, right? Like, so Starlink is a great example of that. We're putting up thousands of satellites in orbit. The Chinese just announced they want to put up something like a 20,000 satellite constellation to compete with Starlink. And so we have lots and lots of rockets going up. We are starting to see the limitations of it. That technology is starting to mature. We're also looking at the moon and Mars missions. Now, in the case of the moon, rockets can get the job done, right?
And rockets work better on the moon. There's 1/6 gravity, so there's
So there, but we're also starting to see that peak. We're starting to see it. It's like, okay, you know what? We're starting to run into some headwinds here.
Yeah, well, there's a moment where the cube square law is going to catch up with the rocket equation, and you can't go any bigger at a certain point.
Yeah, and so I think I see an evolution, and I think this is a good thing, because I don't think that our community, right, this alternative propulsion community, has to compete with NASA or SpaceX or the status quo. The way that I see it is a natural progression. Yes. Where when they hit maturity and they start to really realize that they have limitations, our community will be able to fill in the blanks for them.
I agree with that wholeheartedly. Which is definitely something, like I said, which is what I appreciate about the whole APEC community, is like, we have people, they're not just tunnel visioning on one thing. We're sampling to see what does work, and that's, at the end of the day, that's science, right?
Well, and then another aspect of that too, and this is a little bit tangential, but even today there are applications for this technology. So Drew Arigma and Dr. Charles Buehler down at Exodus Technologies, I was there earlier this week. They are looking at using their technology for satellite orbital adjustments, and in that case, it's not necessarily a limitation of the rocket propulsion speed or anything like that. It is a limitation of satellite fuel, where it is just difficult, costly, and cumbersome to basically send up fueled satellites or refuel them. And so they're hoping to provide something that produces just a tiny field effect force to eliminate a whole lot of fuel.
Are you familiar with the Mighty 1 mission, MITEE-1?
Which one is that? Is that IVO's?
It's basically they do like a little MHD tether very high up in the ionosphere, and that gives it just enough lift where it can stay in orbit low.
Ah, okay.
So it's basically electrifying it's basically taking, because the ions are going to interact with an electromagnetic field, so they do it just right where it can basically grab onto those ions and push itself up at just enough to where it just keeps itself in the right orbit going forward. But I guess we're also digressing here a little bit, but not necessarily, because their whole point of that is that you can keep satellites in orbit without fuel, just based off with the energy you have coming off the solar panels.
Yeah, and I think it is digressing a little bit, but it does highlight the fact that industry has been looking for alternatives to rockets. I mean, the limitations of rocket technology have been known for 100 years.
And we're lucky we don't have a stronger gravitational well on the planet either, else it'd be that much harder.
Yeah, so, it's definitely not, this is not something that's taking, this is not sideswiping industry, but it's also something that in practical terms they can work around right now, and so they're just not dealing with it. I think when they reach the point of wanting to deal with it, things like you talked about, the MHD experiment, that is something that they'll be looking at, but I think that's an area where again, some kind of gravity control, gravity modification, some kind of warp drive technology is going to start to become a more pressing need. And that takes us back to your area, right? So
to a degree. And so there was I forget the name of who it was, but it was another talk like this that you recorded with someone. I think it was in Huntsville, when they were talking about the public deserves to know at very least what our best ideas are.
That was Nick Gold.
Nick Gold. Okay. Yeah. Okay. Yeah. So you and really, we already have those answers out in the public domain of what the government thinks the best answer to explain all this is. That came in the release of the OSAP documents that I've been in part referencing. According to the government, an Alcubierre-like solution or like effect is our best idea that we have towards that. So, everyone right now is pushing for, we want disclosure about what you guys know about NHI. We want to know about what guys know about the UAPs and the reverse engineering programs. What if reverse engineering programs aside, and if whether or not that's a different conversation, but let's just assume that we don't, for the sake of this conversation. But we know we have this leading answer off where to go with things. Well, we need to start drafting legislation around. We need to bring blue skies research back into, paying universe. Hey, figure out this metric engineering propulsion. We're just going to throw money at it until you guys figure it out. I mean, that's what we did in the 50s, and it got us to the moon. So there's ways that this can work. Just people need to start asking the right questions to the right people, and right now most people are not doing that, which is a shame. But some of the answers are there. We have enough answers to at least point to the direction forward, that we need to go forward. And to me, that's.
Well, and I think that answers the initial question, which I think your answer is yes, warp drives are something that we can move towards.
Yeah. So that being said, okay, we now know to take the warp drive notion seriously. What are some implications of this? Let's just follow the math and the physics and see where it might lead. And one of the things that leads to is, so let's talk about the G-forces. You can get 5,000 Gs observed. That was the Tic Tac. Okay, well, based on what we know about the solutions, if you can dampen the G-forces where you can do that without splattering yourself against the hull, you also have a bubble that should be capable of superluminal travel.
Well, and actually that takes me to something that has been kind of a concern of mine. So I am, I'm good friends with Dennis Bushnell, right? He's a human factors, NASA LRC chief scientist. And one of the things that he has expressed is when you are traveling at these speeds, radiation, which is accelerated relativistic velocities, becomes incredibly lethal. And so, your warp drive spacecraft, I'm hoping, can create a bubble around it to either redirect or just block that radiation, because otherwise it's very likely that your astronaut would just be cooked nearly instantaneously, right?
Well, even if it's not just the blue shifted radiation that's cooking you, let's just think about like a regular relativistic rocket. Say if we want to go to Alpha Centauri and we're going to get to 99% the speed of light to get there, and it'll take 4.5 years from an Earth's observer point of view, but it only takes about 3 months or whatever from our particular reference frame. Okay, what happens if you hit a micrometeorite going that fast?
Yes,
that's bad.
Or space dust. Space dust.
Yes.
And it's known that you'll hit space dust, right? I mean, just stray, hydrogen, helium atoms, things like that, just tiny little particles. And, if I remember right, there are only 1 or 2 of them per square meter or even less. But when you're going that fast, right, it's like a shotgun blast.
Yeah, and then this is something that Sarfatti talks about a little bit, is that you can make like a, from the blue shift side, you can almost make like a white hole force field in front of the shield. And really, I don't like that analogy, so I'm going to go to a slightly different one. We need to understand what's happening with the geodesics. Do you know what a geodesic is?
Yeah.
Okay, so when we're following the geodesics of, you know, these photons or anything, when we're manipulating space-time, say your ship's here, your particle's no longer going to go here, it's going to go
around it.
Around it. And so right there, that already solves our problem for shielding.
Yeah.
So we can take care of the g-forces, we can take care of the speed, we can take care of the shielding. Just the warp drive concept on itself already solves a lot of the traditional problems associated with interstellar travel. Now, there's other engineering problems that are going to come with it, but those are different problems, you know. And so, you know, like when we're following the implications of what a warp drive might be capable of, well, let's look at this 5,000 G number for a second. It's just a very quick napkin calculation to figure out how long does it take you to hit the light barrier going 5,000 Gs. It's only about an hour and a half. It's not very long.
Yeah.
And you're doing it in a mechanism which, according to the literature and everything we know about it, is predicted to be able to go with these apparent superluminal speeds. Because remember, inside the bubble yourself, you're not going at all. You know, you're experiencing 0 Gs. Now, there'd be some side caveats. You might be able to make an artificial gravity well in there for comfort of passengers or whatever, but you know, I'm digressing here a little bit.
I think it's absolutely wonderful that you were working through this and working on, I mean, you've been working on the math, working on the calculations, as well as conceptually looking at a lot of different models there. So Alcubierre itself, again, this came out in 1994 when Miguel Alcubierre released the paper. That has been modified many, many, many times.
Yes.
You mentioned that the energy requirements are now being reduced. I've heard other ways that those could potentially be reduced. One of them was, if I remember correctly, spinning the fields may be capable of reducing some of those energy requirements.
Potentially.
So there are a lot of different approaches there.
Well,
so I think what you're saying is warp drive is the way that it goes.
It is the way that it goes. Like it's the only way that these UFOs can work without us having to introduce drastically new laws of physics. It just so happens that these fit the bill perfectly. Like if the shoe fits, it's probably it's Occam's razor dictates that this is the way to go.
And that shows that the media, I wouldn't say that the media is ignorant. I would say that they're taking shortcuts in the way they describe it.
At the end of the day,
defies the laws of physics, not true. Follows relativistic physics, absolutely true.
Yep. And it's no, like most of the media, they're not going to spend time studying relativity in order to understand it. So I do give them some leeway there. I just wish, I know, I wish they would. I wish they wouldn't. But following, and then this is starting to get into some of the more the speculative work that I've been kind of getting into here, is if we're taking this notion of superluminal travel seriously, and as per relativity, if you're going to go faster than light, that is going back in time. Now,
I was going to ask about that because there were a couple aspects of it. There is, I think Sarfatti describes closed time-like curves, which is, you know, I believe that's tied to what you're going to talk about now. You were talking earlier about the possibility of jumping timelines.
Yeah, you can do either. Yeah, you can. You can do either, and I'll get into that. So when you go back in time, there's a bunch of rules and caveats that you're. It's a break it, you bought it type situation, right? There's all these implications and baggage that come with it, and most people view them as bad. I view them as a feature.
Now, that being said, if you're in the closed environment of a warp drive ship, you know, at least when you're in the process of travel, you're less likely to cause a lot of trouble, right?
What do you mean?
Well, I mean, when you're talking about time travel, you get into stuff like, you know, what if you killed your grandfather? You're going to
okay. This is exactly what I was getting into. So this is what I mean about this is a very break it, you bought it scenario. So you're keying in perfectly.
Yeah.
So you mentioned the grandfather paradox. This is a great one for people who don't know what the grandfather paradox is. Say I jump in my warp drive, I go back in time, and I kill my grandfather before my parents were even born. How did I go back in time if I was never born in the first place? You know, that's a paradox. Another one is like a bootstrap paradox. Let's say I let's see, what's the textbook way to...
You take a warp drive back in time and give yourself the warp drive to, right? I think
yeah, so that would be a boot. I guess the analogy I was going to go off is like, say you went back in time and you had a letter that said study physics, and you go and you... Actually, let me rewind on this analogy. Let's say you're walking down the street one day, and then just some old guy pushes you out of the street because you're about to get hit by a car. He gets hit by the truck instead, and then he gives you this letter that says study physics, and you're like, well, this is this guy's dying wish. I might as well at least do what he says. And then you start studying physics, and you figure, oh, time travel, and then you end up building a time machine, and then you have this letter, and then you go, and then you put, who wrote the letter? Where did the letter come from? It's been there the whole time. It doesn't have an origin. That is the bootstrap paradox. And we could do a whole lecture just going on, lists of paradoxes that might come up of out of faster than light travel. Well, there are two ways to solve these. Potentially. One is the Novikov self-consistency conjecture, where essentially there's no free will, and the universe is just one big timeline where everything happens the way it was supposed to happen because that's how it's always happened. And it's kind of a wishy-washy hand-wavy way to word it. Now, in a series of papers by Dr. Barak Shoshani, he goes and he stipulates that if, let's see, there's the known recondition. Yeah, starting with his 2019 lectures on faster than light travel and time travel, and then he goes and he builds into a series of papers where he basically goes and demonstrates mathematically with some rigor if time travel and faster than light travel is possible, then multiple histories must therefore be possible, because that is the only way that you can solve all of these paradoxes. Now, there are some paradoxes that you can solve with just Novikov's conjecture, but eventually, if you start going down the list, eventually you're going to run into a paradox that can't be solved by Novikov. Okay, great. There's a paradox. Our models are incomplete. Perfect. Introduce multiple timelines. Okay, where the hell do multiple timelines come from? This is going to be the many worlds interpretation of quantum mechanics first. Actually, first, this is interesting because people call it Hugh Everett's theory. Hugh Everett III, he wrote his thesis paper was published, the short version, in 1957, but actually Schrödinger was the first person to think of this. Now, Schrödinger's cat was originally thought of as a thought experiment to disprove his own theory. Basically, you have your vial of poison, and next to a piece of radioactive material.
So the cat is both alive and dead.
Yeah, and so
if I understand correctly, the QM interpretation that came out of that is basically the cat exists in a superposition of states, and so it doesn't necessarily violate QM, but there's also this idea of timelines. In one timeline it is dead, in another timeline it is not.
Well, and so what Schrödinger originally was using this analogy for was saying, look, my equation is saying that basically the cat splits into two cats that are dead or alive, and things don't split into two. This is impossible. Like this theory has to be wrong, right? And so that's where his thought experiment originally came, and he used that in the Solvay conference in 1927. Give him some time to cook on this idea for a while. And actually, the Solvay conference is where basically you had Schrödinger and Einstein on one side against Bohr and Heisenberg on the other, and they had the debates back and forth, and eventually the Copenhagen interpretation of quantum mechanics became the textbook one that we end up teaching most people teaching in our textbooks for the next 100 years. It's where you basically have a wave function evolving according to the Schrödinger equation when you're not looking at it, except for when you look at it, then it collapses to a particle and it obeys the different laws of physics. It's kind of wishy-washy hand process. Everyone agrees that Copenhagen's incomplete. Nobody agrees on what the right version is. Fast forward to 1952, and I do have a copy of this. I do have a transcript of that in this one right here, but I'm not going to pull out and look for the quote and read it off. But essentially, so 1952, Schrödinger is now in Dublin giving lectures, and one of his lectures, he starts off with a preamble. What I'm about to tell you may seem insane, or ludicrous. I forget the exact terminology. I'm paraphrasing. And he goes into say, like, if we just look at the mathematics of my Schrödinger equation and what's happening with this, it seemed to saying that really we do evolve into multiple timelines. Now he didn't explore this in any mathematical rigor. He was just kind of suggesting, look, if we take it seriously, this is what my equation is saying. So fast forward into like 1955, you have Hugh Everett III, who is a graduate student of John Wheeler at Princeton. And he starts writing his theory of the universal wave function. That was the original title of his first long thesis, which ended up getting shortened down and then was republished later. But that would become what was popularized as the many worlds interpretation of quantum mechanics.
Okay.
Okay. So bringing this back into warp drive to some degree, and Shoshani's papers, the only way that faster than light travel works is the only way that you can make this happen without giving rise to all these paradoxes, which suggest that the model is incomplete, is that you have these other timelines and that you're exploring these other timelines. Now, there are some timelines where you can form a CTC, a closed time-like curve, and you can end up back in that same branch, or you can explore other ones. You know, there's going to be navigational equations and tricks that we're going to learn down the line. Eventually, we haven't figured those out explicitly yet, but you know that there's work to be done. This is a work in progress. And so my whole thing is like, okay, let's take this notion seriously. All the physics and the math seem to be pointing in this direction. We're gonna need to find a way to account for these in our equations, right? Because we don't want to get lost, right? You know, like I was saying earlier, we don't want to go punch at Chewy and end up in the wrong timeline with Germany 1 or something like that, because that's gonna be bad for, you know, a bunch of reasons that we don't need to go into, because it's an alternate history scenario, and that's just, you know, digressing out of the purviews of this conversation. When you're looking at things from this context and this point of view, the mathematics work out fine. They're consistent. They work. I'm not going to say they're perfect, but they're pretty damn near perfect. And it's something that we're going to need to start from the right we're going to need to start from the right formulation of quantum mechanics if we're going to get all this done together. Now, where most people come in, and we kind of touched on this a little bit earlier off camera, is that general relativity, our theory that we know has worked in every single prediction, it doesn't work with Copenhagen quantum mechanics, that collapse postulate where it collapses back onto a single eigenstate. If we just assume a wave function evolving according to the Schrödinger equation, or the or something similar to the Dirac and Wheeler-DeWitt equation, we can find, general relativity pops out from the entropy of this math as an emergent property of it. And so that should be the way that we're going in with this. And so this is still a work in progress, and there's work to be done. And we need people that are going to help, that can solve super complex, you know, dynamic equations of motion.
But that's the path forward.
Yes.
Well, and on that note, why don't I thank you very much for your time, because we've given people a lot to chew on. We've gone through some very big concepts. So thank you for giving us kind of this overview of warp drive and you know, some of the paths to get there and some of the challenges that may be involved with it as well.
Thank you.